So welcome back, everybody. Last time I was still continuing on with more Euler, which is kind of an impossible temptation to avoid. So I only have a couple more things that I wanted to talk about when it comes to Euler. So one, we had previously noted the following for the Platonic solids. So remember. That for the Platonic solids we had this. Maybe I'll even bring back the little chart that we had. So here was our study of Platonic solids or Pythagorean solids, and we looked at this little table here, right? So we were interested in these Egyptian fraction sums here. Right, so we were interested in these Egyptian fractions, but also we noted E, F, and V, where E is the number of edges, F is the number of faces, and V is the number of vertices. So we actually went through and computed that for these Pythagorean or Platonic solids, and showed that they satisfied this relationship, right? We did this for the cube, tetrahedron, pyramid. Uh, um, and these just a prism, whether they were regular or not, to see if there's any kind of relationship between them. And we found that in every example, F plus V minus E was 2. Okay, so we did this really early on in the semester. All right, so it turns out that Euler was the first to actually notice that. Okay, and it's not just a fact that's true for the Platonic solids. It's actually true for convex polyhedra in general. Okay, and so here is another fact due to Euler. If a convex polyhedra, or polyhedron, yes, is the singular, has V vertices, F faces, and E edges, then the number of vertices plus the number of faces minus the number of edges is 2 in this case. Okay, so Euler was the first to notice this fact. Why is this true? Well, it's hard to describe that in a quick blurb, but here's my attempt. This weird thing that you're computing here, what are you doing? You're counting, and you're counting things of certain dimensions. So you're counting vertices, which are points. Those are zero-dimensional things. I'm not saying there's zero vertices, they're just zero-dimensional. You're counting faces, and those faces are two-dimensional. And you're counting edges, and those are one-dimensional. Now, it's arranged here. Traditionally, this was how it was written when Euler wrote this. So it turns out, actually, Descartes came very, very close to noticing this, but didn't actually explicitly write it out. So it's possible Descartes also noticed this this pattern, but didn't explicitly write it out. Euler did explicitly write this out. I'm going to rewrite this. I'm going to rewrite this as faces minus edges plus vertices. This is the same thing. And this is 2. And the reason I'm writing it like this is so that it goes from two-dimensional things to one-dimensional things to zero-dimensional things. Okay. So 2D, 1D, 0D, right? It's this alternating sum of some count of objects showing up in each dimension. So we have so many zero-dimensional things, so many one-dimensional things, but where you have a minus sign there. We have so many two-dimensional things. If we were counting three-dimensional things, there would be a minus sign in front of it, and so on. It's this weird alternating sum expression here that I've highlighted here as well. What is this thing that's being computed? It's something called the Euler characteristic. Okay. So it's something called the Euler characteristic. Okay, and this Euler characteristic is an extremely important thing. It's an extremely important quantity. And this, again, just like last time we talked about how Euler worked on the seven bridges of Königsberg problem, Euler, uh, in working on that problem, kind of developed some of the very, very basic first principles of topology, which I had mentioned previously. This is another topological thing. In fact, this is an example of what's called a topological invariant. Okay. And what is a topological invariant? It is a quantity that remains unchanged relative to some topological transformation. I described this previously as this is like the study of continuity. So if we continuously deform the object that we're working on, the Euler characteristic is unchanged. What I'm not allowed to do is any kind of breaking, tearing, anything like that I'm not allowed to do, but I can deform an object and its Euler characteristic will remain the same. So I'm not going to define the Euler characteristic in general, but why is the Euler characteristic of a convex polyhedron 2? Right? So really this statement that Euler said, of course, Euler did not define the Euler characteristic in the more general way that it come to be known. That was done hundreds of years later. But he was the first to write out this, which is the Euler characteristic in this special case of a convex polyhedron. So what is it about like this statement then, if I recast it in terms of Euler characteristic, the statement that faces minus edges plus vertices is always equal to 2 is the statement that a convex polyhedron has Euler characteristic 2. Okay. Now, why is it that that is the case? Well, let's go back to our picture. Remember, this is convex, so regular is not required here. Let's go back to our pictures, okay? If I'm looking at this thing. Well, it turns out that every single one of these things could be nicely, continuously deformed to a sphere, okay? Or that a sphere could be continuously deformed to these things. All right, and a sphere has Euler characteristic 2, which can be computed in some other way. All right, and so the sphere having Euler characteristic 2 tells us, because the Euler characteristic is a topological invariant, so that thing that I did to change the sphere into, say, a convex polyhedron didn't change the Euler characteristic. This thing has to have the same Euler characteristic as the sphere that I started with. But the Euler characteristic of the sphere is 2, so the Euler characteristic of this is 2. Okay. Now that's a kind of black box, hand-wavy, high-powered machinery way of thinking about it, because that wouldn't come about until much later. But that is the idea of what's maybe like the reason why this is going on. But that, of course, was not Euler's original proof of that fact. Okay. So one more fact about Euler before finally moving on is just a couple of these number theory facts that we've actually mentioned previously. So Euler was so active all over, now you kind of get a sense for his impact overall. So Euler also worked in number theory. So he proved a number of results. Here's a couple of things that you're familiar with. So one, he proved that Fermat was wrong. Fermat said that every number 2 to the 2n plus 1 is prime, but it's not the case. This is not always prime. Okay, so recall we actually mentioned this before. So all the way back, let me see, in our discussion, we may have actually done this. I believe we did this on like maybe the second or third day of class. I can't. Oh no, that's maybe we did it when we were talking about constructibility. because Fermat primes are related to which polygons can actually be constructed. But the first one that was known, let me look really quickly. So the first Fermat number that was known to not be prime was f sub 5. So Euler proved that if we're calling this f sub n here, so if f sub n is this thing, he proved that f sub 5 is not prime. He did this in 1732. And he did this by factoring, so 2 to the 2 to the 5th plus 1. If you work out what that is, this is 4,294,967,297. And Euler found that this was factored. This was just 641 times 6,700,417. So Euler found this factorization. So the fifth Fermat number is not prime. So Fermat was wrong. They're not always prime. But in fact, it can also be shown further. Euler also proved what form it had to have. So every factor of this has to have a certain form. So Euler showed something about that. This wouldn't be improved until much later by Lucas. It was improved maybe like 100 years later. So not only was Fermat wrong, he thought that all of these numbers were prime, but it turns out that all of the ones that have been checked past this are also not prime. So the question is whether or not there are any more Fermat primes than the ones that are known. So which is f sub 0 through f sub 4 are all of the prime ones. F sub 4 is 65,537. So 2 to the 16 plus 1 is that. That is the, if you remember, that's the 65,537 gon was this biggest hand constructed by straight edge and compass polygon. Okay, another number theory fact. So every even perfect number has the form 2 to the n minus 1 times 2 to the n minus 1. We mentioned this fact when we discussed the Pythagoreans a long time ago. So the Pythagoreans did not know this. Euler showed that this had to be the case, where 2 to the n minus 1 is prime. Okay. He also showed that if phi of n is the number of natural numbers, so this is the number of natural numbers less than or equal to n, such that the GCD of that number and n is 1, i.e. they're relatively prime. This is called the Euler-totient function, or just the totient function. Okay. But Euler was the first to really work with this in the same way. He showed that if A, or maybe I should say so if A is a positive integer such that the GCD of A and N is equal to 1, then N is a factor of A to the totient function of N minus 1. Okay, where have you seen a statement kind of similar to this? This is a more general statement that includes Fermat's little theorem. Okay, which I stated before. So Fermat's little theorem is the special case when n is prime. Okay. All right, so I did not even get close to like touching on kind of the like all of Euler's contributions, but as you already see, I've spent like the better part of like 2.5 lectures talking about Euler, so there's still a lot to be done there. Just like the mathematicians that came before him, he did not worry too much about convergence. If I do a proof of his Basel problem later, then I'll show you why there's an issue with what he did. So he didn't worry too much about convergence. He knew that convergence was important, and he knew that there were some things that were not quite right with a problem that did not converge correctly. But he, nevertheless, I guess he didn't really know how to deal with it. So he just computed, and of course, the results that he got were perfectly valid. They were the right ones, right? Even if some of the reasoning wasn't 100% legitimate. So anyway, so I'll move on now. Like I said, I could spend a lot more time on Euler, but it's time to move on and finish the remainder of these mathematicians. So the next one is Lagrange. So Lagrange was born in Italy. He was half French, half Italian. His father lost the family fortune through speculation, but Lagrange didn't view that as too negative of a thing. In fact, he said that he'd probably never become a mathematician if that wasn't the case. He'd probably just gone into some family business and never touched math. He was actually converted to being interested in mathematics when he read an essay by Edmund Halley, and this convinced him that math was something worth studying. So already by the age of 23, using Newton's theory of gravitation, he was able to explain why the moon is tidally locked with Earth, right? Why the moon always shows the same face to Earth. So he, by the time he was, in his like early 30s, he was already famous as a mathematician. And so he spent about 25 years in Prussia at the invitation of Frederick the Great. And after Frederick's death, he moved back to France. He lived in Paris, and he was a favorite to Marie Antoinette. He was kind of mixed on the French Revolution because he was friends with Lavoisier, who was guillotined. So he had slightly mixed feelings on it, but he did stick it out. He didn't run off. So he survived the revolution intact. He was actually involved in the introduction of the decimal system for weights and measures, and basically, when it came to this introduction of decimal system, some people pleaded for the advantage of base 12, and he would kind of ironically defend base 11 as something to be used before. Because actually, it turns out that if you use a prime number as the base of your number system, then there's a number of advantages to that too, even though you might, kind of inherently look with disgust at something like a base 11 number system, being so accustomed to base 10, right? Basically, Lagrange was responsible for a number results, some of which you might have actually heard of in your classes. So he ended up, when did Lagrange die? I believe he died in like 1803, 1813. I was off by 10 years. So he was born in 1736 and died in 1813. There's a story about Lagrange and Laplace that's almost certainly apocryphal, but it's not. I think everyone said that it uh, historians have said that it displayed everyone's that was involved in the story's personality like so well that it's impossible not to include it when you talk about him. So I'll mention him again in that context. So he, Napoleon, and Laplace is another mathematician I'll talk about in a second. There's an interesting anecdote about them. So anyway, what are some of Lagrange's accomplishments? So he was responsible for something called Lagrange's theorem. Now, he did not actually prove this, so this is in group theory. And what's funny about Lagrange's theorem is group theory, in the way that it is now understood, was something that came out of the work of Galois, who's a mathematician that's not included in our textbook, but I will include a mention of him as we go into the next material, since the poll results are in and you guys kind of want to see a mix of things. So I'm gonna do that. So group theory wouldn't be fully fleshed out. The basics of group theory wouldn't be fully fleshed out until the 1820s, 1830s. And you see Lagrange was already dead by then. So one funny thing that people often say is when you take your first course in abstract algebra, so when you're in your first undergraduate serious algebra course, the first thing you study is group theory. And one of the first big named theorems that you prove in the course is Lagrange's theorem. And so Lagrange's theorem has something to do with the order of a subgroup of a group dividing the order of the group itself. Okay, so without understanding any of those terms, what's interesting is that Lagrange's theorem was a theorem before group theory was a subject. So it was a theorem in group theory concerning groups about a topic that did not technically exist at the time. And that's to show you that a lot of times you have mathematicians working with an object and they don't fully understand exactly what it is, or maybe what its relationship is to a bunch of other things. And so it won't be fully understood until years later. And so Lagrange's theorem is typically said to be the first theorem in group theory. Okay, so group theory is one of the foundational parts of what is known as abstract algebra. So if you have never had a course in abstract algebra, you can have a look over. It's kind of the easiest way to describe group theory is a nice way of categorizing symmetry. So group theory comes up all the time in theoretical physics. So this is a topic. This is kind of the starting point of that. This is where right around, so after the discovery of calculus, by the time you get to Euler, things begin to explode in directions where the abstractification of math goes kind of haywire, and math expands quickly in all directions to very quickly outpace the technology of the day, right? I mean, if you say you need relativistic calculations to deal with computing things having to do with say satellites or space missions or things like that, but relativity, right? These things were worked out in the early 1900s. So that's it's kind of group theory This stuff was being done in the late 1700s in its very earliest form. It wasn't really worked out until the 1830s. So already, in the 1830s, right, 200 years ago, you're having like the first rumblings of abstract algebra, which is already a sort of math that basically very few people outside of like an undergrad in math or someone that's had undergraduate coursework in a math degree is not going to have seen ever. So, okay. What else did Lagrange do? So he came up with the first proof of what's called Wilson's theorem. Uh, so what is Wilson's theorem? Wilson's theorem is a theorem in number theory that says the following: if P is prime, then it is a factor of P minus 1 factorial plus 1. So that's Wilson's theorem. So a prime number is a factor of P minus 1 factorial plus 1. Okay. What else was Lagrange responsible for? So the first complete solution to the Diophantine equation x squared minus r times y squared is equal to 1. Okay, where r is a non-square integer. It's positive, right, greater than 0. You've seen this equation before. Okay, so this is Pell's equation, right, which was a complete misnaming. Right, the guy Pell never studied this equation apparently. So I believe this was actually I think it was a misnaming due to Euler. Euler for some reason had mistakenly thought that he had done work on it. And so he referred to it as Pell's equation, but this, even if Pell had done work on it, the most amazing solution to this before Lagrange was not due to any European mathematician. It was actually due to Bhaskara. So recall Bhaskara's work and Brahmagupta's earlier work, but Bhaskara kind of took this to the best place. So there was the Chakravala method. So recall Bhaskara's Chakravala method. So Bhaskara had the Chakravala method, which was this way of dealing with this equation and solving it. And it wasn't until all the way in the 18th century that Lagrange comes along and puts the complete solution on solid footing. So from Bhaskara to Lagrange, basically no one had made progress on this at all. Okay, so that's a big deal. He also generalized the way that he gave a solution to this equation to give a complete treatment of Diophantine equations of a general quadratic form. Okay. So that's nice. He was responsible for proving the following. So Lagrange proved that every natural number is a sum of 4 squares. So let's look at some examples here. So every natural number is a sum of 4 squares. So what about 7? All right. So how can I think of 7 as a sum of 4 squares? Well, it is 2 squared plus 1 squared plus 1 squared plus 1 squared. Okay. And you're like, oh, well, if they can repeat, that can't be that hard, right? So 9, for instance, is 3 squared plus 0 squared plus 0 squared plus 0 squared, right? So if we can include zeros, and if these things can repeat, you might think it's not a big deal, right? What's the big deal? Seems like you could easily, come up with 4 for every number. And you might convince yourself that that's easy enough, but the thing is that actually proving that this can be done for every single number is not exactly that straightforward, right? So you can try to think about how you might go about doing that. Okay, so Lagrange came up with the first proof of this fact. Okay, Lagrange is probably the most famous among undergrad math students for discovering the method of Lagrange multipliers. So the method of Lagrange multipliers in multivariate calculus for optimization problems. So these are specifically optimization problems with constraint. Now, in the context of Calc 3, a lot of these constraints are purely geometric. So you have the graph of some function above a region. The region is described as the region inside some boundary curve. And so what you end up doing is you want to find absolute mins and maxes on this region in question. If you got a closed and bounded region, you have something called the max-min theorem that tells you as long as your function's continuous on that region, you're going to be able to do it. You're going to have a max and a min. So the question is, where are they? There's only 2 places they can be. They can be somewhere in the interior, but if they're in the interior, then there's a restriction, and it's called being a critical point. Okay, so this is also true in Calc 1, but in Calc 1, because you're dealing with an interval, a lot of the more complicated stuff doesn't come into play because your endpoints are just 2 points, whereas the analog of your endpoints in Calc 3 and in higher dimensional stuff, you're going to have at least a curve, which is already much worse than 2 points because a curve is infinitely many points, right? So there is no plugging in the boundary in that case. But you got two choices when you're looking for a max or min for such a function on a closed and bounded region. It's either in the interior, but if it's in the interior, it's got to happen at a critical point, and there's ways of detecting those, okay, by derivatives or partial derivatives. The only other option is that it occurs on the boundary of the region. And here's where Lagrange multipliers come in, because typically you didn't care in Calc 1 if it occurred at the boundary, because the boundary is 2 endpoints. So you plug in the 2 endpoints and you're happy. But in Calc 3, you can't plug in the endpoints because there's infinitely many of them on the boundary. And so what do? Well, you do the method of Lagrange multipliers. So the method of Lagrange multipliers is the thing that allows you to find maxes and mins of some continuous function of more than one variable, so some function f of xy or f of xyz, some function of more than one variable. You can find maxes and mins over some closed boundary region using Lagrange multipliers. Okay. All right. So Lagrange was the first to kind of systematically study differential equations. So he was the first to lay down a systematic foundation for differential equations. Okay. So he was the first to lay down systematic study of differential equations. This led to some very interesting discoveries, so I'll talk about that one next. It's going to involve some words you've heard before. He wrote this work called the Mécanique, which he originally thought of doing when he was still 19, but he published it when he was 52. So he published the Mécanique. So at age 52, began working on it at 19. So this was kind of like his life's work. This book contains a ton of stuff, but one of the things that it contains has to do with the dynamics of a rigid system. So consider the following differential equation. So let's say d dt of del t del theta dot minus partial t partial theta plus partial v partial theta is equal to 0. Let me describe what some of these quantities are. So T is the total kinetic energy. V is the potential energy. Okay. T is time. Theta is any coordinate. Theta dot, this is Newton's notation for d theta dt, the derivative of theta with respect to time. Okay, so this Lagrange condition is so Lagrange noted that this boxed expression, that star, really says that the following, the total action is minimal. What is the total action? The total action is the integral from a to b of t minus v dt. Okay. What does it mean for a thing like this to be minimal? Okay. Well, to talk about a quantity like this and minimizing a quantity like this takes something beyond just calculus. So calculus, one of the things that calculus is concerned with is minimizing or maximizing, right? Finding extreme values, finding optimizations of functions. But look at this thing, right? This thing is a thing involving an integral, right? And you're wanting to minimize this over t's and v's, right? What you're wanting to minimize here is a function that takes in other functions, right? So you have a function of a function is really what you are trying to minimize. This is known as a functional. So a functional is a function of a function. What's an example of a functional? So an example is I'm going to give the functional, and I'm going to write it as I of u is the integral from, say, 0 to 1 of u times f of x dx, okay, where this is some fixed function x that this integral depends on. Okay, so what does this mean? So let f of x be, say, x squared. Okay. Then this I sub f of u is the integral from 0 to 1 of u, which is some function of x, d, or u times, say, x squared dx. Okay. And so, for instance, this functional thing, I could plug in x. So if I plug in x here, this functional value would be the integral from 0 to 1 of x times x squared dx. This is just the integral from 0 to 1 of x cubed dx. Using Cavaliere's formula or integration power rule, this is x to the fourth over 4, evaluated from 0 to 1. So this is 1 to the fourth over 4, or 1/4. Okay, but what if I plugged in something else here? So what if I plugged in, say, cosine of x? Well, this would now be the integral from 0 to 1 of x squared times cosine x dx, right? So the x squared is still there because that's my fixed function f here, but now it's cosine x. And to do this integral, I would need to integrate by parts, and I'm not going to do that right now. But I would have to integrate by parts. I would eventually get an answer, but you can see how a function where you plug in another function is maybe something that you haven't considered before, or if you had, it's something that you haven't really studied that much. Because normally, we're used to plugging in single real numbers into functions. So a function of a function, this is an example of what's called a functional. And now, if calculus allows us to compute mins and maxes of functions, what kind of thing would allow us to compute mins and maxes of functionals? Things that look like this, or things that look like this total action that Lagrange was interested in. This requires something called the calculus of variations. So the calculus of variations, I've mentioned this before. When I mentioned this was when we talked about the brachistochrome problem. So to actually suitably solve the brachistochrome problem, you have to do some calculus of variations computations. Okay, so the very first problem in this was the brachistochrome problem, proposed by the Bernoulli, solved by Bernoulli, Newton, and others. This was the first problem in the calculus of variations, but there was no systematic way of studying this. This was a single problem. So the only methods that were used by Bernoulli and Newton, they only applied to that particular problem. There was no systematic understanding of the larger question of how do you minimize a functional. Okay, so the early work in the calculus of variations was done by Euler and Lagrange. This led to conditions known as the Euler-Lagrange equation, which is a condition that is one of the first things you learn in the calculus of variations. It's a really interesting subject, actually. I highly recommend anyone that's even vaguely interested in analysis or mathematical physics is another reason to get into calculus of variations, because it's some really, really interesting problems. And the problem statements are, in many cases, really simple. So doing some calculus of variation stuff is really interesting. So calculus of variations was worked on clearly with the brachistochrome problem. Euler did some work in it. That's why he gets his name on this too. But Lagrange was the first to actually fully write down the basics of calculus of variations, and he did that in the Mécanique and in the context of minimizing this total action integral. And so in order to talk about how this is minimal, he basically had to discover calculus of variations. So this is where calculus of variations came in. Okay, so that was something else Lagrange did. Okay. All right. So, next, we're almost at the end of our 18th century mathematicians. Laplace. So, Laplace ended up eventually being a marquis after the Bourbon Restoration, but Laplace himself finds he finds himself inserted at various interesting parts of history. So Laplace was Napoleon's examiner when Napoleon went to what was the school? So let's see here. Yeah, so when Napoleon went to basically the military academy in Paris in 1784, Laplace was Napoleon's examiner, and for most of his life he remained a friend with Napoleon until Napoleon's downfall. So he was in there. He actually had a government ministry position under Napoleon for a little bit before he was replaced. He was minister of the interior. And I'm trying to find there's a quote that Napoleon had about Laplace. Oh yeah, so yeah, here it is. So Laplace was Minister of the Interior for 6 weeks. He was replaced by Napoleon's brother. Some historians think that was always Napoleon's intent, so it was just a placeholder position. Anyway, Napoleon at least later claimed that the reason he dismissed Laplace was because Laplace was was a terrible administrator, and his reason for doing so is here. So, geometer of the first rank, Laplace was not long in showing himself a worse than average administrator. From his first actions in office, we recognized our mistake. Laplace did not consider any question from the right angle. He sought subtleties everywhere, conceived only problems, and finally carried the spirit of infinitesimals into the administration. So that's Napoleon's assessment of Laplace's governing abilities. But mathematically, Laplace was a lot better suited. So he published a great work. This is Celestial Mechanics. So he published this in I don't have the year here, but Celestial Mechanics was kind of his biggest work that essentially laid out the full Newtonian view of celestial mechanics and the Newtonian viewpoint of the solar system, motions of all heavenly bodies, and really, really nice computations kind of cementing all of that. This basically remained the ultimate work on the overall cosmological physics of the solar system until relativity. So until the late 1800s, this was the tome. And here's another funny note about Laplace from the American translator of Laplace's Celestial Mechanics into English. So the American astronomer Nathaniel Bowditch, who translated 4 of the 5 volumes into English, observed, "I never came across one of Laplace's 'thus it plainly appears' without feeling sure that I had hours of hard work before me to fill up the chasm and find out and show how it plainly appears." So in Celestial Mechanics, he used this phrase over and over, "thus it is clear," or translated another way, "thus it plainly appears," "thus it is obvious." And he apparently was one of the first to actually say this in a mathematical context. So everyone who's been tortured by a phrase like that, knowing that it's maybe not exactly obvious. A lot of times, what is meant is not necessarily obvious. It is straightforward. it is a straightforward computation. I remember taking differential geometry graduate course, and I was reading a text, and it said it is a straightforward computation to show blah. And I had as an exercise to actually fill in the details, and there was like 2.5 pages of really nasty computations to do. It was straightforward technically in the sense that, no giant black box theorem was needed, but still it was 2.5 pages of work taken up by, thus it is obvious or thus it is evident. Another joke is, a physics teacher or a math teacher is at the board and he's writing and he says, and thus it is obvious that, and he stops for a second and he goes over to the corner of the board and he starts scribbling furiously, and he's scribbling and erasing and scribbling and erasing, and after 5 minutes of that he says, ah yes, it is obvious that this is the case. So anyway, Laplace is the one that introduced that mathematically. Laplace has a ton of stuff named after him that you might have heard. So one is the Laplace Transform. So this, most commonly, the first place you come across this is when you first encounter ordinary differential equations. So what's the Laplace transform of a function? So if I have a function f of t, the Laplace transform of little f of t is big F of s, which is the integral from 0 to infinity of e to the minus st times f of t dt. Okay, where this s is a complex number. So s is complex here. Now, that the first time that you're introduced to this, you might not worry about that bit too much. It's treated more of as a formal thing. What is the point of the Laplace transform? It looks like it takes a function and does something really nasty to it, so why would I ever want to do this? In differential equations, you can transform functions. You can transform derivatives of functions. And it turns out that there's really, really nice and simple properties that fall out of this thing when you transform function and its derivatives. So what you do is you start out with a differential equation, you hit it with the Laplace transform, and with a little bit of work, it turns a differential equation, okay, which is hard generally. Differential equations there's all kinds of stuff that goes into differential equations. It's not the same as an algebraic equation. There's all kinds of different considerations. But it turns a problem that is a differential equation basically into an algebraic equation. And if the order of the differential equation is low, so order here refers to how many derivatives show up. So if the order is low, then the algebraic equation it turns it into is not bad. It's easy. It's like a quadratic thing, maybe, or maybe a cubic at most. And then after you've turned it into an algebraic equation, you solve it. And then to go back, it turns out that the Laplace transform is really nice because there is a notion of an inverse Laplace transform that is basically just as nice as the forward direction Laplace transform. So you go back to your solution that you seek for your differential equation. So this is really useful. It has a ton of awesome properties, and Laplace is the one that discovered this. Okay, so he gets his name on it. He also wrote out the Laplacian. So what is the Laplacian? So if I have a function, we'll say, of 3 variables, so let's call it little f of x, y, z. Okay. So I have a function of 3 variables. Just like there are derivatives of a single variable, when you have a function of 3 variables, or more than 1 variable, we'll say, there's not a notion of the derivative anymore, but there is a notion of partial derivatives. So it's a derivative with respect to one of the variables. Okay, and so since there's partial derivatives here we can talk about, there's a particularly nice combination of these things. So if I take the double x partial, okay, of xyz. So this is the second order partial with respect to x. So it's the x partial of the x partial, okay, of xyz. And add to that the double y partial of my function xyz. And add to that the double z partial of my function xyz here. Then this expression can be rewritten as this delta f, where this delta is the Laplacian operator. Okay. It's important because there is an equation, Laplacian of f is equal to 0. This is called Laplace's equation. This is extremely important because functions satisfying Laplace's equation are known as harmonic functions. And harmonic functions are extremely important in a number of applications, like signal processing and, well, tons of stuff. This is also a quantity that shows up all over the place in descriptions of the differential equations that govern all sorts of things like waves, diffusion, the dispersal of heat. Okay, all can be described using the Laplacian. So I'll do that next time. I'll finish up with Laplace, and then we'll start on kind of the free form stuff, kind of just touching all the topics that you guys might want to see. So that's it. We've basically finished the official material in the course, and we're going off the rails officially next time. So I will see you all on Monday.